class of loaded system of first order partial differential equation. Introduction. The study of boundary value problems for loaded differential equation and system is dictated by numerous applications in gas dynamics, shell theory, magnetic hydrodynamics, electron scattering theory, groundwater prediction, mathematical biology, and other fields in practice. Is known as node into many phenomena in complex evolutionary system with memory consequently depend on the history of the system. Such phenomena are usually described by loaded differential equations. Let omega be the rectangle omega parallelepiped with. We denote omega 1 1 equals omega 2 1 equals omega 3 1 equals gamma 1 1 equals gamma 2 1 equals gamma 3 1 equals.
Yeah, the same one.
In omega, we consider the system of equation 1, where A x, y, z, B x, y, z, C x, y, z, D I x, y, z, F I x, y, z, E equals 1, 3 are given function in omega. U x, y, z is the noun function. U x0, y0, z0 is the value of u at a point x0, y0, z0. Loaded differential equations and our determined system with regular, singular, and supersingular coefficients were studied, for example, in 112. In this paper, based on the method developed in 268, we study the loaded over-determined system of partial differential equation with regular coefficients. Problem: find an explicit solution to the system of loaded differential equation 1 by using arbitrary constant and prove the unique solvability of a Cauchy type problem. First equation is basic. we say that the first equation of the system 1 is basic if we start by finding a solution of the first equation and then substitute the obtained solution into the second and third equations. Let the first equation of the system 1 be the basic equation, then write down its solution as equation 2, where WA x, y, z equals integral 0 to x a t y z dt. Now we write the second equation of the system 1 in the next form. In the next form 3, where WA and WB x, y, z equals integral 0 to y bx s z ds equals 3. Instead of u, x, y, z, substituting its value from 2. We have next 4. Before differentiating equation for preliminary, we demand the fulfillment of the condition. Five, differentiating equation 4 and taking into account the condition 5. After we have some simplification, this 6 from the condition independence of the left part, 6 from the variable x, we get 7. Transforming the last term of equation 6 according to 7 to determine phi of y z, we obtain the equation 8. Having differentiating equality 7, after some simplification, we get the next expression. Expression 9. Further, the third equation of the system 1 can be written as 10, where WC x, y, z equals integral 0 to z, c x, y, z ds. Substituting the expression 2 for u, x, y, z into 10, taking into account the condition 11. And differentiating the equality term. After some simplification, we obtain the expression 12. Since the left hand side of 12 is independent of the variable x, we get 13. To determine phi y z, we transform the last term of 12 according to 13 and obtain the differential equation 14. So to define an arbitrary function phi y z, we get over determined system 8 and 14. Differentiating and simplifying the equality 13, we find 15. Subcase 1. If in the system of equation 8, 14, the first equation is the basic fundamental, then its solution is according to 6, will be written in the form 16, where b 0 y z equals integral 0 to y, b0 is s z ds. Now we write the second equation of the system 8, 14 in the next form 17. By 16, the inequality 17 can be written as 18. Before differentiating equation 18, we first demand fulfillment of the next condition 19. Having differentiated equation 18, after some simplification, we get the expression 20. since the left hand side of 20 is independent of the variable y, we get next 21. To determine mu1z, we transform the last term of 20 according to 21 and obtain the differential equation 22. As now, the solution of equation 22 can be expressed as 23, where WC 00 z equals integral 0 to z c 00 zeta d zeta. S1 is an arbitrary constant. Now, simplifying equality 21 have 24 in omega 1, 1. Substituting the values of phi yz and mu1z from 16 and 20, 30 into 2, we obtain the integral representation of a solution of the system 1 in the form 25, where R1 x y z equals B1 x y z equals D1 x y z equals 7 u x0 y0 z0 are known constant numbers. From the equality 25 at x0 at equals x0, y equals y0, z equals z0, we obtain the algebraic equation 26. To find the condition 7 and u x0, y0, z0, we state the following initial value problem. Problem K1. Find a solution of the system 1 in the class C1 omega satisfying the initial condition 27, where P1 is a noun constant. Using the integral representation 25 and the initial condition 26, we get this 28. Thus, to determine the constant C1 and u x0, y0, we obtain the linear algebraic system 26, 28. Solving the system 26, 28 by Kramer's method, we calculated the corresponding determinants, and consequently we get 29, 30, where M1, M2 are the corresponding values of determinants of the system 26, 28. Thus, we have proved the following assertion. Theorem 1. Let the coefficients and right-hand sides in the system of equation 1 satisfy the following conditions. 2a, 2b, 2c and 2d and 3. Then the problem K1 has a unique solution in the class C1 omega, and this solution is expressed by formula 25, where C1 and U, X0, Y0, Z0 are calculated by formula 29 and 30. Remark 1. Assertion similar to theorem 1 for the system of equation 1 are obtained when the second equation of the system 8 and 14 is the basic equation. Remark 2. Statements like theorem 1 and remark 1 for the system of equation 1 are obtained when the second equation of the system is fundamental. Remark 3. Assertion similar to theorem 1 for the system of equation 1 are obtained when the third equation of the system under consideration is the basic equation. References. Thank you for your attention.